Hello, in this video we study moments and center of mass of some variable density planar lamina. Okay, suppose we have the following lamina and we want to find the moments and the center of mass of this lamina. So usually we know we need to break this lamina into small pieces, right? And then we need to find moment of each small piece. Look at this picture. We have Ri, where Ri is some square, right, in our partition. And that is corresponding to the point xi, yi, right? So we know the mass of this Ri. The mass of this Ri is nothing but rho of xi, yi, right, times delta ai. Okay, where rho is the density in that neighborhood. Okay, we suppose that the density in that neighborhood is constant. Makes sense? And that is equal to rho xi, yi. And the area of this Ri is just delta ai. So since we have mass, we can find the moment. We can the moment of mass of Ri. Okay, from here you can find the moment of mass. The moment of mass is equal to rho xi, yi delta ai times yi. So if you look at this picture, right, times yi, where yi is the distance right here. That is the yi. So this is the moment, right, of rotation about the x-axis. Makes sense? And you know, you have to multiply the mass with the distance from that point to the x-axis. That's why you have to multiply with the yxi, the yi right here. Agreed? So I will write the moment of the mass with respect to the x-axis. Makes sense? So similarly, you can find the moment of mass with respect to the y-axis. So for the y-axis, that should be equal to rho xi, yi delta ai times xi, where xi is the distance from that point to the y-axis. That is the xi. Makes sense? All right, now we have moment of mass in a small piece of that partition. In order to find the moment of mass, you know, of the whole lamina, we just integrate that. Right? We write the Riemann sum and then you do some limit process. So basically, from these two formulas, you can find the moment of mass with respect to the x and the y-axis of some lamina. Let's generalize this. From here I have, you know, the moment of mass, right, of the whole thing, that is equal to double integral on r rho xy in here, and since here you have yi, you multiply with the y right here, okay, and then dA. Similarly, you have the moment of mass with respect to the y-axis equal to double integral rho of xy in here. Here you have x and then dA. Is it? So that is the only difference, right? Remember, the mass is what? It's double integral on r rho x and y dA without y and x. You see that? And then the moment of mass with respect to the x, you multiply with the y right here, but with respect to the y, you multiply with the x right here. Okay, so let's consider the following example. We have some lamina y less than equal to 4 minus x squared and greater than equal to 0. Okay, and they ask us to find the center of mass. Once you have the moments of mass with respect to the x and the y axis, you can find the center of mass of the lamina. Okay, you can find the center of mass. That is x, y with the equal to m y over m, mx over m, where m is the mass of the lamina. Okay. So basically, in order to find the center of mass, you need to find the moment of the mass with respect to the x and the y axis, and then the mass of the lamina. Here is one thing we have to remember. The x coordinate is equal to my. Makes sense? Where my is equal to this. This is my. Okay, here is mx. The moment with respect to the y will serve as the x coordinate, right, of the center. That makes sense because, in the formula of my, what you have? My is, from the x with respect to the y, right? So you just multiply with the mass with the x distance right here. You see that? With the x distance right here. So basically, that will give you the x coordinate. Makes sense? If you find m with respect to the x, so you multiply with this guy, right? This guy will give you the y coordinate. So that's why the center of mass looks like this. Makes sense? Don't forget this. That is not mx over m, but my over m and mx over m. Okay? All right. Let's consider the following example. You have some lamina, and here's the form of the lamina. Okay, and that is, y greater than or equal to 0, less than or equal to 4 minus x squared. 4 in here, negative 2 here, 2 in here. So that is our lamina. They ask us to find the center of mass. Okay, where the density at point xy is proportional to the distance between that point and the x-axis. Okay, so we have to pay a little attention. Here is 0, and let me write a sentence where the density is scalar multiple of the distance between xy and the x-axis. I remember in one example, we saw that the density is scalar multiple of the distance from that point to the origin. But in this case, that is scalar multiple of the distance between that point and the x-axis. Okay, so what is that? Suppose you have some point x, y in here. What is the distance between that point and the x? That is just the y coordinate, right? That is just the y coordinate. So basically, this sentence gives you rho x and y equal to c y, where c is a constant. Make sense? Okay, so let's solve this problem. We need to find 3 values. First, we need to find the mass. M equal to double integral on r. The function is c y, okay, and then dA. You can pick the order dx, dy, or dy dx, whatever you want, okay. But let's do that with the cy and then dy dx. Okay, so if we integrate with respect to the y first and then the x, I need to fix x. Make sense? I need to fix x. So when I fix x, I make some, a vertical line right here, and I can find the interval where the y change, right? For each x. So basically, y will go from 0 to 4 minus x squared. Make sense? In this order, it's easier to find that, because you don't have to solve for the x. If you write in the form dx dy, means you have to fix y, right? And then you solve for the x. That takes more time, because right now you already have the function y equal to 4 minus x squared. That is a very good experience. Make sense? So I will integrate with respect to the y first. Y will go from where? From 0 to 4 minus x squared, and x goes from -2 to 2. My integral looks like -2 to 2c, and here I have y squared over 2, evaluated from 0 to 4 minus x squared dx. And then we have c over 2, -2 to, at 0 the function is 0, so I just have 4 minus x squared and then square dx, right? And I have to open this. I have c over 2 and then -2 to 2. I have 16 minus 8x squared plus x to the 4th and then dx. So I have c over 2. The first term is 16x. The second term is minus 8 over 3x cubed. And the last term is x to the 5th over 5. And this evaluated from -2 to 2. And then you plug the number -2 and 2 into this function, you get 256k over 15. So this is the mass of this planar lamina. The next value is the moment with respect to the x. So the moment of the mass with respect to the x equal to double integral on r rho, which is cy times y, okay, dA. If you find the moment with respect to the x, so you have to multiply with the y. Don't forget that. I mentioned right here, okay. So similar to the previous case, we can rewrite this as integral from where to where. Let me see. Integral from -2 to 2, and then we have c right here, and then we have integral from 0 to 4 minus x squared and y squared dy dx. Okay, so let's find this out, and then we have -2 to 2. We have y cubed over 3 evaluated from 0 to 4 minus x squared dx. Okay, and what's that? That is c integral c over 3 from -2 to 2 4 minus x squared cubed dx. So here we have to open parentheses right here. Okay, let me write it down. A minus b cubed equal to a cubed minus 3a squared b plus 3ab squared minus b cubed. So if you apply this for a equal to 4 and b equal to x squared, you would have the following one. 64 minus 48 x squared plus 12x to the 4 minus x6 dx. And you use the power rule. You have c over 3. This gives you 64x. This is 3x cubed over 3, 48. And here you have 12x to the 5th over 5 minus x to the 7 over 7, evaluated from -2 to 2. Okay, so basically that is equal to 4096c over 105. That is the moment of the mass with respect to the x-axis. Similarly, you can find, the moment of mass with respect to the y-axis. Let's do that. So you have the integral of r cy times x dA, right? And then of course you can separate that. That is from -2 to 2, from 0 to 4 minus x squared, cy here, and yx dy dx. Okay, so we integrate with respect to the y. In this case, we cannot rewrite this in the form of product of two integrals, given that you can separate y and x, but we have integration limits for minus x squared right there, so there's no way to write in the product. We have to find integral, so you have c -2 to 2. The function is x y squared over 2 evaluated from 0 to 4 minus x squared dx. So you have c over 2 -2 to 2 x 4 minus x squared and square dx, right? Because at 0 the function is 0. So you have c over 2. Here you have -2 to x 16 minus 8x squared plus x to the 4 dx. And then you have c over 2 -2 to 16x minus 8x cubed plus x to the 5th dx, right? Overall you get c over 2. This gives you 8x squared. This gives you minus a over 4 x to the 4, and this gives you x to the 6 over 6. Okay, so this is 0. Why? Because all functions in here are even, right? All functions in here are even, and you have integration limit -2 to 2. So when you plug 2 and -2 into this function, you have the same value, and then you subtract them, you get 0. All right, so the moment with respect to the y is 0. Why? Because our lamina look like this. It is symmetric with respect to the y-axis. You see that? So that means, the moment with respect to the y is 0. Agree? So that is very natural. From now, we already have mx, my, so we can find the center of mass of this lamina is my over m, mx over m. My over m is 0. Mx over m. What is mx? Mx is right here. And what is m? M is right here. So I have to copy this and divide them. Let me write here so I can follow that. And 96c over 105 divide means multiply by the inverse 15 over 2, 56c. I'm sorry, here should be c, not k, okay? Should be c. So c with the c will be cancelled out. Overall, you get the number 16 over 7. So that is the y coordinate of the center of mass, 16 over 7. That's how we can finish this problem. Okay, so basically you need to remember the formulas, and again you need to know how to rewrite a double integral in terms of iterated integrals. Make sense? The moments of mass are sometimes called the first moments. At the same time, we still have the moments of inertia, which is called the second moments. Okay, the moment of inertia about a straight line is a measure of the tendency of matter to resist a change in rotational motion. So the moment of inertia can be described as I equal to m d squared, where m is the mass and d is the distance from that point to the straight line. Okay, Similar to the case of the moments of mass, we can find moments of inertia using this idea. So the moment of inertia with respect to the x-axis is equal to m d squared, right? So if I generalize to the case of double integrals, I have m, the mass is equal to double integral of rho x and y, and then we have dA in here, right? And the d in this case, the distance from that point to the y-axis, so that is y squared. Remember that? So if you have mx, right? So that is just the 1y, right? Because here you have only d. But if you have the moment of inertia with respect to the x, so here you should have y squared. And similarly, you may find the moment of inertia with respect to the y. I write d in here, okay? Here I write dx, here what dy. So that is double integral on r rho x and y times x squared dA. Makes sense? So, you know, that is what we need to do right now with the last example. So that example would be very similar to previous case. The only difference is x squared and y squared right here. Okay, so let me continue the previous example. Let's find the second moment. Find the second moment, or find the moment of inertia. Okay, the second moment. So I have ix equal to integral from where? From -2 to 2, and here from 0 to 4 minus x squared, and you have cy times y squared dy dx. All right, I just copy, you know, what we did previously in here. Here's the integral, but this is with respect to the y, right? So you multiply with the x, and here you multiply with the y. Okay, let's solve this to the end, and then we finish today's lecture. That is equal to -2 to 2. Here we have cy cubed, so I have y to the 4 over 4, evaluated from 0 to 4 minus x squared, and here's dx. And then you write -2 and 2. At 0, the function here is 0, so I only have c over 4 right here. That's 4 minus x squared to the 4 dx. And you have to open this parenthesis, right? You get c over 4 in here, -2 and 2. I have 256 minus 256x squared plus 56x to the 4 minus 16x to the 6 plus 6 to the 8 dx. And then you integrate this, you get c over 4. This gives you 256x minus, here you have 256 over 3x cubed, and here you have 96 over 5x to the 5th, and here you have 16 over 7 x to the 7. Here you have x to 9 over 9, evaluated from -2 to 2. So basically, you know, all functions in here are odd. You just need to find, you know, the function value at 2. At -2, you have the negative of that function value. So overall, that would be equal to 32,768 c over 350. Okay, so, you know, this is nothing but just multiplying, you know, the first moment with the distance. Make sense? That is just, you know, the first moment with the distance. So you get the second moment, which is the measure of the resistance. Okay, so if you have any questions, just let me know. And of course, you are welcome to solve this problem to the end to find IY. Okay, if you have a solution, please send that to me for extra credit. Thank you, and see you in the next video.